The question becomes now, when we measure electricity at home, what are we going to use, coulombs or amps? Well, I think many of you have heard of amps before, and unlikely any of you have heard of coulombs. You can ask your parents about this. So unless you are on battery power, all of our electricity never runs out, so it's a current source. So you never actually care about the total. Okay, it's not going to run away. So if you're hiking and you go, well, we only have 1 liter left, or in your car, you have 10 liters of fuel in the tank, totals are important. But if it's in a pipeline and it never runs out, then it's the flow rate that's important. Think about a garden hose compared to a fire hose. The only difference is the flow rate, but neither of them can run out of water. However, if you use a battery powered device, the total charge is important. And when you get billed for water and electricity each month, you pay for the total quantity that was used, not the rate of flow. Let's look at it in terms of finance. You get paid $10 an hour. This is a current or flow rate of money. Let's call this minimum wage and make a symbol for it, big W. And we'll call it wager units. You work for 6 hours. This is the time. Using normal math, quantity is the rate times time. So you would take $10 an hour times 6 hours and get $60 total. What if we used it in wager units? Well, then you would take this $10 an hour and turn it to 1 wage unit. This is really the equivalent of sort of an astronomical unit. All the scale stuff I'm teaching you and things, it moves, it's transportable to any unit. So we're going to sit there and call this 1 wager unit. And now the total quantity of money you get is 1 wage unit times 6 hours gives you 6 wage hours, 6 wager hours. It looks weird, but it does report a total quantity. Or if someone, let's say you had a really weird rate of pay, and a person says, I'm paying you $17.14 for 21 and a half hours. And you say, well, how much money is that? And you go, I just said $17.40 times 21 and a half hours. That is a total. It's just presented to you in a really obnoxious fashion that requires you to do math. Let's look at it in electric units. 10,000 coulombs again, and let's set a flow rate of 1 coulomb a second. How long is this going to take to drain? Well, I think you understand the time for something to drain must be the quantity over the flow rate. I mean, again, turn it to money. I have $10,000 and I'm spending $1 a second. How long do I have my money for? 10,000 seconds. Okay? So I get 10,000 seconds before this tank of electrons drains. But 1 hour is 3,600 seconds. This means 10,000 seconds divided by the seconds in an hour is 2.7 hours. So this battery can provide a current of 1 amp for 2.7 hours. So what I've done is calculated the time in 10,000 seconds. But then I have to put the time in hours, because who wants to be told, please wait for 10,000 seconds? So I convert that flow rate, or the time it took the flow to completely drain the tank, and we work out that it took 2.7 hours. Now we got 2 choices here. We can tell the public that 10,000 cups of water drained out of the tank, or we can say the tank was leaking at a rate of 1 cup a second for nearly 3 hours. And you go, well, it doesn't really matter which way you say, does it? Except for one problem. What if nobody understood what a cup was? All they'd ever seen is running water. Most people in the public have never heard of a coulomb of electricity. So to say to them, careful, 10,000 coulombs of electricity passed through the crowd. And you go, is that a lot? So instead, what they're telling you is something really weird. They say it's 2.7 hours, 1 amp runs for 2.7 hours. and they stack the two together. And again, the bottom line, which I can't move to, or that little pop-up window will block it. This battery is a 2.7 amp hour battery. What it's saying is this battery kicked out 2.7 amps of electrons in an hour. 2.7 coulombs per second flow for a full hour. And it's going to take you a little bit of time to get that through your head, that what we're reporting is, this would be the equivalent of me saying, well, how much money am I getting paid? And you say, dude, you're getting paid a standard wage unit for an hour. So if I said to you, you're being paid $14 an hour for 6 hours. So I would say 14 times 6, and I would get a total and say, or I'd say 14 times 6. I'd say you're getting 14 for 6 hours, and you have to calculate the total. Okay? Now, all of these batteries, except the one on the right, have the same voltage, 1.5. So the 9-volt battery doesn't apply here. These 4 batteries here are beautifully designed because they look exactly what they are. They're canteens. So which of these batteries holds more electrons? I think that's pretty obvious. The D battery holds nearly 4 times the total compared to the AAA. But if these are water tanks and you punched a hole in the bottom, the flow rate, what would come charging out, there wouldn't be any more pressure in any of these tanks because they're all pretty much the same height. So you can largely judge a battery by its size, providing they have the same internal structure and the same chemistry. So let's compare a typical value of what these can do. A D battery can produce 12,000 milliamps for 1 hour. These are real numbers, okay? What's a milliamp? It's like a millimeter. So if this was 12,000 millimeters, it's 12 meters. So this battery can produce, I got a mistake in this. It doesn't matter. It's actually 1.2 amps. But let's call it 12 amps for 1 hour. And you kind of go, oh, I get it. It can produce 12 coulombs a second for a full hour. This one, that's 8 amps. It can produce 8 amps for an hour. This one, milli, is only 2.7. Okay? And this guy can only do 1.2 for 1 hour. So if you look at this number compared to this number, the flow rate is 10 times bigger. So I've made an attempt to make this line a tenth the size of this one. Okay? So what this means is the D battery is capable of dumping out 10 times the flow of a AAA battery, or it can produce 10 times longer at the same flow rate. So the big difference between these 4 batteries is that the time they operate, or how much flow they can produce at a given time. Here are some sample calculations. What is the total electric consumption of the following? A 200 amp clothes dryer runs for 2 hours. 18 amp hair dryer is on for 15 minutes. And a 300 amp car battery cranks for 45 seconds. This battery shown. Okay, so this is where we'll be going on our next step to see how we solve these problems. And here's the simplest way to do it. Change that letter A to cups per second. And the minute you do that, you will solve these. If it still doesn't work, I want you to take this and turn the 200 to either liters per second or dollars per second, not hour. And the minute you do that, you will solve these instantly. As written, they may confuse you. And the solution is getting rid of amp and turning it to what it is, cup per second, and you will realize you can solve these almost in your head, and then we will take them up later. And I would encourage you to watch these videos because it shows you incidences of some of our new generation batteries that they explode and they have lots of energy in them, making them rather dangerous. And the last Star Wars movie, Solo, they were dealing with